Alright, so in the last video I pretty much went through the code and the basic functions of the code. So in this video I'm going to relate to how we can use these graphs to better create better filtration systems. And so we have the last graph, which is velocity distribution as a function of x, and this is basically showing as the velocity is increasing, as distance is increasing. So this basically means that the water molecules are entering the tube, and this makes sense to start off at 0 because it just entered a filtration system, which basically slows down all the water molecules and passes them through layers. I think it was nano-sized holes in this one, and then as this went on, as it flows through the tube, the water molecules picked up its velocity. And what that last graph showed us is that basically as the longer the tube, the more the x velocity will be as it reaches the end of the tube, and that could possibly lead to the water molecules passing through that last filtration system faster. And this is the path of an atom. This is interesting because when we calculate pressure, we are using density times height times the gravity. So density and gravity will be almost constant throughout. I say almost because the ones at the bottom will be a little bit more dense than the atoms at the top, because the ones at the top are putting more pressure on the ones at the bottom. It's kind of like how the water molecules at the deep sea level are more dense than the ones at the top. And so by looking at this, we can basically get a general idea of how the pressure is fluctuating for the atoms. And if we wanted to find an individual atom, we can go and change that and find that. And then for this one we have volumetric flow, and then or nanometers cubed per picosecond. And this mirrors the velocity, so it's entering the filtration system, so it's going to be basically starting off at 0, and then as it flows through the tube, it's going to constantly increase at a constant rate, or increase at a constant rate. And we see the same thing with mass flow. And for pressure of atoms as they flow through the tube, we can basically get a general idea of this just by looking at the path of an atom as it flows through the tube. We have our height, and we just multiply the height by gravity by density. This just gives us these exact numbers of pressure. So if we wanted to look at that relationship, we can use this graph. The pressure of atoms as they flow through the tube, or more like the pressure acting on the atoms as they flow through the tube. This could be important because it's basically telling you how dense some of the how dense some of the water flowing through the tube will be, and this will basically tell you as it for the filtration system on the outlet, basically how many water molecules will you have to accommodate for to flow out of to leave the tube. So if this is very dense at the bottom, then you might want to create smaller holes so you can accommodate for the extra water molecules that are gonna be at the bottom. And this is basically pressure of the first and last atom relative to their x-coordinate. So this is the pressure as a function of distance, which is basically what we just looked at. Well, yeah. And then this is the mean. So if you just wanted to get a general idea of, I guess this is the mean pressure. So yeah, the average as a function of time. So how the pressure fluctuates over time, and if you wanted to make the water flowing through the tube either more dense or less dense, this information can be useful, so you can see what's changing over time and what's causing the pressure to increase. More pressure would mean that the water will be more dense, and then less pressure will mean that the overall density will be lower. And this is basically the pressure of all of the water molecules as they progress over time. And you can use this data for the same reasons that we used for the previous one. Thanks for watching.